So we want to determine whether each of the experiments given is a binomial experiment, where we want to specify the appropriate pieces n, p, and q, if so, and the possible values of the random variable x. Meanwhile, if not, we want to see why they are not. Where our two cases are that a certain surgical procedure has an 85% probability of success, and a doctor performs the procedure on 8 patients with the random variable representing the number of successes. Where in the second case, we have that a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. We select 3 from the jar without replacement, and the random variable represents the number of red marbles. So in the first case, essentially what we want to do here is think about whether this fits our criteria to see that this is binomial. The first thing we want to check is whether or not we have a fixed number of trials, and in this case we're told that we take n equals 8 surgeries. So, first property is met. Usually the first one's going to be met. It's kind of free if we're checking these things, but it's still good to be sure. Next, we're going to assume that these are independent trials. Like I talked about in that video earlier with the multiplication rule and the ACL surgeries, it might not be fair to assume that the doctor's performance isn't affected by previous surgeries, but we're going to assume, I guess, some robotic competency here.
I am Dr. Perceptron. Let me give you something to help you relax.
That a successful or failing surgery doesn't affect the next one in any way. So these will be our independent trials as we need, and then we need to talk about what a success or a failure looks like in this case. Where here, a success is actually a good thing. It's a successful surgery. Even though I have it right in front of me, I am blanking on how to spell surgery. There's too many similar sounds in there. Where, in particular, we are given that P is that value 85%, 0.85. On the other hand, a failure is, again here, kind of clearly a bad thing. That would be a failed surgery, where that, because P is 0.85, we'll have probability Q is 0.15. Complement. So, we're good on all of our pieces, and we gave a perfectly valid definition for X, that X is a number of successful surgeries. So, accordingly, this is a binomial experiment. We've got all the things that we need. On the other hand, for our second run, looking at this, we do have a fixed number of trials. We're drawing n equals 3 marbles from the bag, but these are not independent trials. That's a very important property here, that the trials be independent, that drawing one shouldn't affect the others in any way. But because these are not, because if you draw one and don't replace it, all of the probabilities are affected, this is not a binomial experiment. Even though every other piece of this would be met, because those values for P and Q are not consistent values, we can't make this work. Now, it'd be very easy to adjust this to make it a binomial experiment. All you'd have to do is just replace the marbles every time. You put it back in, now it's fine, because every time you put it back in, the probabilities restore back to where they were, and you have what you need. But because we're drawing without replacement, we are drawing without independence of events. So this cannot be a binomial experiment. And next, we're going to take that formula I talked about a bit earlier and expand it, generalize it, show it in such a way that we can find any binomial probability as we would need, assuming we actually are looking for a binomial probability, that is.